Hey everyone, and welcome to The Explainer. I am so glad you're here. Look, today we're going to totally strip away the sci-fi, cut right through the hype, and look at the actual reality behind what is honestly one of the most exciting tech shifts of our lifetime. We're talking about redefining the very limits of computation by seeing what happens when quantum mechanics actually meets modern high-performance computing. Let's get right into it.
So, to really understand where we're headed, we kind of have to ask a provocative question first. Are our current supercomputers hitting a wall? Now, I know, it sounds a bit crazy to ask that when we've got these modern exascale chitons like Frontier and El Capitan. I mean, these are magnificent machines, right? Pumping out over a quintillion calculations per second. But here's the truth. Despite building these absolute behemoths, we are still slamming into an impenetrable wall of classical intractability. When we try to simulate the fundamental nature of the universe, like, say, the exact quantum mechanical behavior of a complex molecule, our classical computers, no matter how massive they are, they just choke.
Okay, let's dive into this. If you look back, the history of high-performance computing is really just a series of architectural paradigm shifts. Back in the 1990s, we moved to massively parallel CPU clusters. Then, around the 2010s, we realized, well, CPUs just couldn't do it all, so we brought in GPU accelerators to handle highly parallel math. And of course, that eventually sparked the whole AI revolution. Which brings us to the 2020s. The next logical step in this evolutionary timeline isn't about replacing what we have, it's about bolting on an entirely new kind of engine. We are literally entering the era of quantum-centric supercomputing.
Section 1. The supercomputing bottleneck. Let's take a closer look at those classical limits.
So, the limits of classical computing. They're becoming very, very real. We all know Moore's law is slowing down, right? We just can't shrink transistors forever without running into massive heat and power density issues. But honestly, the bigger problem is the combinatorial explosion. Think about it. If you want to do an exact molecular simulation, using an exact method called full configuration interaction, which tries to account for literally every single electron interacting with every other electron, the compute power you need scales exponentially with the size of the system. Trying to map the quantum states of electrons onto classical binary bits is just incredibly inefficient. To put it in perspective, a 50-qubit circuit simulation requires matrices with up to 2 to the power of 50 entries. That's massive. It instantly overwhelms the memory of even the largest classical supercomputers on Earth.
And because of this specific bottleneck, several absolutely critical fields are fundamentally stalled out. We're talking high-fidelity material science, strongly correlated molecular simulations, massive combinatorial optimization problems, think global logistics and supply chains, and, of course, advanced cryptography. These fields demand a completely new type of processing horsepower because they are inherently way too complex for just zeros and ones alone. They need a system that actually speaks the native language of nature.
Section 2. Meet the quantum coprocessor. All right, we need to get familiar with a new acronym here. The QPU, or Quantum Processing Unit. Let's be crystal clear about something. Quantum computers are not these magic standalone boxes that are going to eventually replace the laptop on your desk. Not at all. They are highly specialized computational accelerators. They leverage the bizarre, wonderful rules of quantum mechanics, specifically superposition, which is like being in multiple states at once, sort of like a coin spinning in the air, and entanglement, where qubits are inextricably linked no matter the distance, to explore vast computational spaces simultaneously. Basically, they're built to solve very specific, classically intractable subproblems.
And this is a really crucial distinction to make. The myth out there is that quantum computers are standalone replacements for classical computers. The reality? Entirely different. The true future is hybrid quantum classical coprocessors. You see, a QPU's true power is really only unlocked when it teams up with classical supercomputers. You use the QPU for the exponentially difficult quantum math, and you use the classical CPUs and GPUs for the data prep, error mitigation, and workflow orchestration. They're partners, not competitors.
Section 3. The hybrid hardware architecture. Let's see how this future is actually wired together.
Now, what's really interesting about this evolution is how we integrate these systems. We started out with standalone models. This was super loose integration where you manually prepare a problem, then send it off to some isolated quantum computer over the web. Next, we moved to co-located models. These are cloud-based, they're automated, but they still suffer from the high latency of network communication. You're still waiting around. But the ultimate goal? The absolute holy grail, that's on-node integration. We're talking incredibly tight integration using standard buses like PCIe or CXL directly inside the high-performance computing environment.
Imagine seamlessly linking cryogenic QPUs, operating just a fraction of a degree above absolute zero, directly with liquid-cooled classical server racks. It's wild.
And within that true quantum-centric supercomputer, there's a very strict division of labor. Think of it like a highly specialized team. The CPU acts as the general manager, handling the workflow's scheduling and data pre-processing. Then, the GPU steps in for the heavy lifting on tensor math, AI, and gradient estimation. Next up, we have FPGAs. These guys operate at blistering speeds, handling real-time pulse control in hundreds of nanoseconds and doing the error decoding. And finally, the QPU steps up to execute the actual quantum circuit. Every single component does exactly what it's best at.
Section 4, the software integration stack. Let's talk about unifying that architecture.
Obviously, to make this actual usable hardware for scientists, we need a unified architecture blueprint. At the very top, we have the application and middleware layer, tools you might have heard of like Qiskit or NVIDIA's CUDA-Q. These allow developers to write a single script in, say, C++ or Python. Simple enough. Next, that script drops down to workflow orchestration, using familiar high-performance computing tools like Slurm, which essentially treats the QPU just like any other compute node. Finally, the system automatically partitions that single script, sending the classical tasks to the GPUs and the quantum circuits right over to the QPU for hardware execution. It's totally, beautifully seamless.
And I gotta say, this seamless, tight integration, it's absolutely crucial because of how the most promising algorithms actually work. Take variational algorithms, like the Variational Quantum Eigensolver, or VQE. These things are highly iterative. The QPU runs a circuit and measures an output. Then, a classical GPU takes that output, optimizes the parameters, and fires them right back to the QPU for another run. It's a continuous, rapid-fire back-and-forth feedback loop, and it requires ultra-low latency. This is exactly why specialized high-speed interconnects, like NVQLink, are being developed right now. They ensure deterministic latency straight from the controller to the accelerator.
Section 5. Unlocking impossible science. Let's get into the massive real-world stakes here.
Jay Gambetta, the director of IBM Research, recently gave some massive industry validation for this exact approach. He said, and I quote, "The future lies in quantum-centric supercomputing, where quantum processors work together with classical high-performance computing to solve problems that were previously out of reach. The industry is totally 100% aligned on this. The hybrid model isn't just some stepping stone, it is the definitive future of computing." And this brilliantly illustrates what happens once logical, error-corrected qubits actually start running inside these hybrid HPC systems. The breakthroughs become incredible. We're talking about accurately simulating the FIMOCO cluster. That's an enzyme active site that could literally allow us to synthesize green fertilizer at room temperature, which would completely revolutionize global agriculture. We can design complex high-temperature battery materials by directly simulating electron interactions. We can accurately compute binding-free energies, meaning we could screen tens of thousands of drug candidates in weeks instead of years. We could even optimize entire multi-step chemical plant processes end-to-end. It's a total game changer.
But we do have to pivot our tone here for a second, because this next part is vital. With great power comes a very real ticking clock for global cybersecurity. We are fast approaching what is known in the industry as Q-Day. Think about it. The exact same hybrid supercomputing systems that can simulate a complex molecule, yeah, they can also be used to run algorithms that crack the cryptographic foundations of the entire internet. A standard data leak is bad enough, but a completely quantum-broken authentication system, that is catastrophic. 10,000. Just 10,000. That shockingly low number is the amount of neutral atom qubits that recent research from a company called Oratomic suggests is required to break P256 encryption. You might be wondering, why so low? Well, it's because progress is aggressively compounding right now. The hardware is improving, error-correcting codes are becoming vastly more efficient thanks to highly connected qubits, and the software algorithms to crack encryption are being continuously, relentlessly optimized. And this rapid acceleration in hybrid quantum capabilities has completely upended the timeline. 2029, that is the actual year major tech companies, like Cloudflare and Google, are now targeting for full post-quantum security readiness. This is not a distant problem for the 2030s anymore. The realization that quantum accelerators will scale inside supercomputing centers way faster than standalone systems has pulled Q-Day significantly forward. So, I want to leave you with a provocative question to chew on. When quantum accelerators finally unlock the impossible, will your data and your industry be ready? We are literally standing on the edge of the most profound shift in computing since the invention of the transistor. The hybrid quantum-centric supercomputer is here, it's scaling, and it's absolutely going to change everything. Thank you so much for joining me on this explainer. I hope you found it as incredibly fascinating as I do. Keep learning, stay curious, and I'll see you next time.